Hi, this is the third class of our Materials for Photonics course. In this class, we will review optical properties of materials and mainly glasses. Good work! Do not forget to answer the quizzes. These are images from the south of Brazil, more specifically images from Rio Grande do Sul, our beautiful state located in the south, making frontiers with Uruguay and Argentina. There you will find the best barbecue in the world. You will also see people drinking chimarrão in the streets, at work, relaxing in parks, everywhere. Chimarrão is the hot water infusion of erva mate that gaúchos, those born in Rio Grande do Sul, drink all the time. It's very good to the health. It's very good for everything, like they used to say. It's also the state of beautiful landscapes, modern cities, good universities, and nice people. I hope that you can visit Rio Grande do Sul when coming to Brazil. So, let's start our class on basic optical properties. Let's start by giving you another important link to those interested in glasses. At Lehigh University in US, you will find the International Materials Institute for New Functionality in Glass, IMI. The International Materials Institute for New Functionality in Glasses was established in August 2004 through an initiative of the National Science Foundation for enhancing research collaborations between US researchers and educators and their counterparts worldwide. It's also a collaboration between Lehigh University and Penn State University. The IMI is coordinated by our dear friend Professor Himanshu Jain from Lehigh University. You can contact him directly or go to the Institute website in order to get more information or even apply for a scholarship to work with them. They also offer online courses like this one, and in fact you will see that some slides presented here were adapted from a course given by Professor Pierre Lucas from Arizona State, US, in glass properties. We will talk about optical properties of glasses. Optical properties obviously refer to the consequences of the interaction of the electromagnetic radiation with materials. You must remember that light propagates in space. Two perpendicular fields, the electric and the magnetic, propagate at the well-known light speed. In silicate glasses, this velocity is about 30% lower. In fact, we will see that the ratio of the light speed in vacuum and in a given material defines what we call refractive index of that material. Optical waves propagate through insulators and do so with some characteristics determined by the dielectric constant and refractive index of the material, and by any absorptive or scattering process. As a result, insulators have a broad window of transparency over some part of the optical spectrum. In this transparency window, the dielectric constant generally has a weak dispersion, therefore the material transmits light with very little loss. Wavelength outside the transparency region can induce strong polarization processes that cause a dispersion in the dielectric constant or refractive index, with an associated increase in propagation loss or absorption. Ordinary glasses are highly transparent and visible for three main reasons. 1. Their polarization processes are either too slow or too fast to keep up with the oscillations in electromagnetic fields associated with the visible optical wave. Consequently, the refractive index is only weakly dependent on wavelength in that region of the electromagnetic spectrum. 2. Their constituents do not have electronic states that allow free electron or bound electron transitions in the visible. And 3. Their microstructure is homogeneous and isotropic, and their refractive index is dependent on neither spatial position nor direction. If we look at polarization processes, we see that insulators can undergo several major changes in polarization over the electromagnetic spectrum. All such changes will affect the dispersion refractive index and cause absorption. These changes consist of polarization processes associated with the following structural excitations: orientational or dipolar polarization. If polar molecules are present in the insulator, thermal agitation keeps the dipoles randomly oriented. Applied electric fields will align the dipoles. This alignment takes a certain time, tau p, characteristic of the orientational motion of the polar molecule. Ionic polarization. The core electrons around each ion and valence electrons involved in bonding are polarizable through a slight shift in the electron cloud and the ionic core, leading to the formation of induced dipoles. The characteristic time for distortion of the electronic cloud, tau I, is much shorter than the orientational polarization time, tau p. Electronic polarization. Valence electrons can be photoexcited out of their bonding states, providing free electrons that contribute to the polarization as in metals. This process is very fast, and its characteristic time, tau e, is much shorter than tau I or tau p. In between these regions of resonance, the polarization processes are either too slow or too fast for the incident electromagnetic wave. In the case where the polarization processes are too slow, the molecules or electrons do not have time to respond to the applied oscillating field, so they cannot extract energy from it. In the case where the polarization processes are too fast, the ions or electrons react immediately to the change in direction of the applied oscillating field, and remain in phase with it. Again, this does not lead to any exchange of energy or absorption. Only when the period of the wave matches the reaction time of the polarization process, there is an exchange of energy. In this case, as the field is applied, the dipoles begin to reorient. However, by the time they have aligned themselves with the field, it has changed direction. This maximizes the phase difference between the applied field and the induced polarization, leading to maximum energy extraction from the wave. The refractive index and absorption coefficients are affected in a way similar to that for the induced polarization, as shown in the figure. Normal dispersion corresponds to a decrease in refractive index with increasing wavelength. Anomalous dispersion refers to the opposite behavior. In other words, in the normal dispersion regime, the higher frequency light will travel more slowly than the lower frequency light. A monocrystal will have optical properties defined mainly by the optical constants. Optical quality is good, but they are difficult to prepare. Polycrystalline insulators have microstructure that can have additional effects on transparency. If multiple phases are present, or in the presence of grain boundaries within a single phase, strong scattering processes may occur from any region with a sharp change in refractive index, and this scattering makes the insulator opaque. Another source of opacity in insulators can come from dopants that absorb light through bound electron excitation. Transition metal and lanthanide oxides are important examples of such absorbing species, and they add color to insulators. Ordinary glasses are transparent in the visible region, as already mentioned. The interesting thing concerning glasses is the freedom of chemical compositions. We used to say as a joke that you can add all the periodic table to your glass. In fact, we can tune by the chemical composition in which region of the spectrum they will be transparent. Moreover, glasses are also much easier to prepare, in most cases, of course. Light incident upon an insulator undergoes several processes besides the dispersion during propagation already mentioned. Still related to the refractive index is the property of birefringence, which is the variation of the refractive index between different polarization directions. Glasses, as isotropic media, do not present that property. Considering a glass, one can observe reflection from any boundary that is associated with a change in refractive index, absorption, scattering, absorption and elastic re-emission in random directions, and therefore the transmitted beam will be affected by all these mentioned processes. Reflection will be given by the Fresnel equation, which takes into account the refractive index and the extinction coefficient. In the transparent region, the extinction coefficient is zero, and therefore the refractive index is given by this expression. The reflection will be given for low angles by this simple relationship. It means that if the refractive index is around 1.5, the reflection at each surface will be around 4%. Absorption will decrease exponentially with z, the optical path, and the absorption coefficient, alpha. The relationship between the absorption coefficient and the extinction coefficient is given by this expression. Scattering also decreases exponentially with z, the optical path. The scattering coefficient is proportional to the inverse of the fourth power of the wavelength. This plot gives the intensity of scattered light as a function of the wavelength. This is the Rayleigh scattering, which results from microscopic fluctuations of the density. Light is then sent to multiple directions. There is no energy transfer to the scatterer. Rayleigh scattering is the explanation of the color of our sky. Why is the sky blue? This is the first question of our quiz. Scattering from particles is independent of the wavelengths. It's given by the Mie scattering. So the change of sky color at sunset, red nearest the sun and blue furthest away, is caused by Rayleigh scattering by atmospheric gas molecules, which are much smaller than the wavelength of visible light. The gray-white color of the clouds is caused by Mie scattering, by water droplets which are of comparable size to the wavelength of visible light. Transmission, therefore, is defined by the reflection and absorption. If the optical quality is good, the scattering may be discarded, and so the transmission will be given by this expression. Still with our basics, let's distinguish reflection and refraction. As you know, our Indians living in the Brazilian forests know very well the basics of optics. They know very well that the fish, peixe in Portuguese in the figure, is not where it looks to be, thanks to the Snell-Descartes law. French say Descartes law, British say Snell law. Let's be peaceful and please both French and British and call the law Snell-Descartes law. This law relates the incidence angle theta and refractive index n. A very important consequence of the Snell-Descartes law for us is the possibility of having total internal reflection. For example, if light propagates from a medium 2 to a medium 1, if the refractive index of the medium 2 is larger than the refractive index of the medium 1, always that theta 1 will be larger than theta 2. For a given angle, theta c, the refracted beam will be parallel to the surface. Θ1 equals 90 degrees. We call this angle critical angle, and it will be given by the ratio of the two refractive index, 1 and 2. For any angle θ2 larger than the critical angle, light will be completely reflected to the medium. This process is what we call total internal reflection. We will come back to this to explain light guiding in optical fibers. The deviation a light beam will suffer will depend on its relative velocity in the two media. This defines the refractive index as the ratio of the two velocities. For example, in ordinary glass, the velocity of the light is 200,000 kilometers per second. If we take the velocity of light in vacuum, this gives a refractive index of 1.5. As a general information, this table gives the refractive index value for some materials we use every day. Have you ever heard about metamaterials? Well, things begin to be a little bit strange when the refractive index is negative. Yes, it can be negative. Of course, this is not related to natural materials. But the material can be structured in a way that the effective refractive index can be negative. Our Indians would face problems fishing in a medium with such a refractive index. In this review, available at the school website, we will have a taste on this interesting and very hot subject. We will come back to it later. We have already commented here about the dispersion of the refractive index with the wavelength. The dispersion is in fact a very important property for someone interested in materials' optical properties. In the transparent region, dispersion is normal. In resonance region, the dispersion is anomalous. The refractive index values goes in fact to infinite. This figure shows typical dispersion curves for optical glasses of high, medium, and low index. An universal parameter proposed in this sense is the Abbe number, defined here. The Abbe number is also frequently referred to as the V-value, the nu value, or the reciprocal dispersive power. One can see that the lower the Abbe number, the greater the dispersive power, that is, the greater the chromatic dispersion for a lens, for example. Various families of glasses fall within well-defined ranges of Abbe numbers and refractive index, as shown in the figures. This is the same plot where the classification of different glasses is shown. If nu is lower than 50, we call the glass a flint glass. If nu is larger than 50, the glass will be a crown glass. Glasses can then be categorized by their composition and position on the diagram. This can be a letter number code as used in the shot glass catalog as shown in this figure. Abbe numbers are used to calculate the necessary focal length of achromatic doublet lenses to minimize chromatic aberration. In practice, the dispersion can be fitted to the Sellmeier equation if some values of refractive index are known for some wavelength. The parameters A, B, and C are then treated as adjustables. While written for one-component glasses, the equation is normally used for multi-component glass compositions. There are several ways to measure refractive index. This is the Abbe refractometer. It measures the angle of incidence required to just begin total internal reflection for light propagating from a standard glass hemisphere of higher index to a sample of lower index. This is the minimum deviation prism goniometer. Is the most accurate method for measuring refractive index. So we just need to position the source to one side of the unknown prism and measure the minimal angle of deviation. We rotate the prism 180 degrees and repeat the measure. This gives a measure of 2 times delta m, from which the refractive index can be calculated. This is the prism coupling method. A prism is coupled to the sample surface. Laser light incident at the prism surface at an angle corresponding to angles lower than the critical angle will lead to total reflection of the light and maximum light intensity at the detector. By changing the angle of incidence of the laser, when the critical angle is reached, light will enter the sample, and therefore the intensity of the light at the detector falls down. Knowing the refractive index of the prism, and by using the Snell-Descartes law, the refractive index of the sample can be determined with accuracy comparable with that of the minimum deviation method. The picture shows the equipment we have in our lab with 3 different wavelengths available. These are refractometers. The method consists of the measurement of the angle of a mirror required to send a collimated optical beam back along its incoming track. The refractive index of the V block must be known to the same accuracy as the desired for the unknown sample. An ellipsometer is usually used to measure the thickness and the refractive index of films deposited on a substrate. With an appropriate standard, the same method can be applied to index measurements on bulk samples. This is the general scheme of an ellipsometer. So, a monochromatic light is passed through a polarizer and a quarter wave compensator to give elliptically polarized light. This light is incident upon a sample surface at a specified angle. The reflected light is then detected through an analyzer, and both the polarizer and the analyzer angles are varied to find the maximum extinction of the reflected light. The values obtained consist of the polarizer angle, the analyzer angle, and the angle of incidence. The backline method is most used in optical mineralogy. Small glass fragments in an immersion liquid of known refractive index are observed under a microscope. As the microscope stage is moved away from focus, there will be a bright line contouring the perimeter of the glass sample. This is the backline. If the refractive index of the immersion liquid is lower than that of the glass, the backline will move inside the object when the distance between the objective lens and the specimen is increased. Decreasing the distance will cause the backline to move outside the sample. If the immersion liquid index is higher than that of the sample, the backline will move in the opposite direction. Different liquids are used so as to bracket the unknown index. The bracket is narrowed until the desired degree of accuracy is reached. A femtosecond laser can also be used to measure refractive index. The white light pulse from a titanium sapphire femtosecond laser is used. By decomposing the transmitted pulse into its component colors, the time taken for each wavelength to transmit through the sample can be calculated, giving the refractive index for each wavelength directly. Accuracy is good, to the second decimal place for a sample 1 mm thick. Considering thin films, refractive index and thickness can be obtained together by using transmission-reflection spectra, ellipsometry, or prism coupling. This figure shows a typical absorption spectrum of a silicate-based glass. It shows the absorption coefficient as a function of the energy and wavelength. In fact, all dielectric materials will display a spectrum with this V shape. The first thing to note is the huge variation of the absorption coefficient, 10 orders of magnitude. You also see that the visible range is a small range of the x-axis. The spectrum runs from the UV to the infrared. The absorption edges at both sides are governed by fundamental processes related to the material chemical composition. In the UV side, the increase in the absorption is due to the electronic transitions related to energy difference between valence and conduction bands. The energy gap is usually obtained from the edge position. In the infrared side, the increase in the absorption is due to the multiphonon transitions. This is the language of physics. You remember that for periodic structures, crystals, phonons with energy of vibrational motions propagate in the material. In glasses, lacking long-distance order, we used to say that phonons cannot propagate. They are localized. I prefer the chemistry language in this case. Localized phonons characterize, in fact, molecular groups. The vibrational modes are molecular ones. The multiphonon process refers then to the harmonics of the fundamental vibrational modes. Therefore, the exact position of the minimum in absorption will be dictated by the chemical nature of the glass. Silica is transparent and invisible, as everybody knows. However, the minimum in absorption is not in the visible range. The minimum in absorption for silica glass occurs around 1.5 micron. That is therefore the wavelength of choice for telecom signals. This is the bottom of the spectrum. It shows the minimum occurring at 1.54 microns and indicated as the third telecom window, where, as we said before, the telecom signal runs. The spectrum also shows the second and first windows used before. First, second, and third windows tell us the historical evolution of telecom signals. You can also see in the figure the attenuation units used by telecom and fibers people. Decibel, or dB, is the unit used to report losses. It is related to our well-known chemical absorbance. The number of decibels is 10 times the logarithm to base 10 of the ratio of the two power quantities. You can also observe the peak occurring at around 1.49 micron for silica fibers. It is in fact related to OH groups occurring, and not desirable, in silica. 1 ppm of OH in silica fibers lead to 4 dB per kilometer at this wavelength. New methods of fabrication of fibers claim to remove these residual OH groups. Coming back to the spectrum, you see that for 1 centimeter of optical path, absorbance of silica glasses in the visible range is 5 times 10 to the minus 5. A normal spectrophotometer that we use in our lab is not able to measure such a low absorbance. Our spectrophotometer here in Araraquara is able to read values of absorbance of 10 to the minus 4. And in addition, as we already said, the visible is not the region of minimum absorbance. In the infrared, considering 1 centimeter optical path, the absorbance of a silica glass will be 10 to the minus 7. For 1 centimeter optical path, this is really nothing. But consider an optical fiber. For 1 kilometer of optical path, this means 96% of the initial light intensity, arriving at the end of the fiber. You see that the signal would experience an important attenuation for some kilometers. This brings us to the second question of the quiz number 3. The first one was about the color of the sky. Do you remember that? Araraquara is around 270 kilometers from the city of São Paulo. If 1 watt of power at 1.5 microns is injected in a fiber here in Araraquara, what is the power that will arrive in São Paulo? Consider for this calculation the attenuation value of 0.2 dB per kilometer. To calculate this value, you will just take into account the intrinsic absorption for silica, which is 0.2 dB per kilometer. Of course, In the real world, the attenuation is composed of different terms such as scattering loss, bending loss, radiation loss, leaking modes. We'll come back to this talking about optical fibers. The V-shape spectra can be calculated for different materials by taking into account the Rayleigh scattering losses at the high energy side and the multiphonon losses at the lower energy side. This figure, taken from Wikipedia, shows that kind of calculation for the fluoride-based Zeblanc glass compared to real values. The figure also shows the shift when Zeblanc and silica are compared. This figure shows the same kind of spectrum for different materials. The transmission window for different glasses will therefore be determined by the chemical nature of the glass. In this figure, you have the transmission window for silica and germanium selenide glasses. You see that germanium selenide glass is transparent above 10 microns, suggesting applications in infrared devices, such as night vision devices. The transmission window spectrum is in fact a composition of spectra obtained in two different equipments. Spectrophotometers are usually operational from the UV to the near infrared. FTIR, Fourier transform infrared spectrometers, operate in the infrared. Spectrophotometers typically cover a range of wavelength from around 180 nanometers in the UV to 3000 nanometers in the infrared. This region includes the UV, the visible, and the near infrared. Light sources are the deuterium lamps used in the UV range, and tungsten and halogen lamps used for the visible range. Monochromators use gratings. Detectors, we use photomultipliers, charge-coupled devices, silicon semiconductors for the visible, and semiconductors in the infrared, indium gallium arsenide and PBS. In the infrared, interferometers are used instead of dispersion monochromators. A lot of sensitivity is obtained by using this. This is the interferometer. It consists of two mirrors and one beam splitter. The infrared light is sent half to a fixed mirror and half to a moving mirror. The light resulting from the light coming from both mirrors is sent to the sample. The interference pattern obtained with the different positions of the mirror gives the interferogram. The interferogram is modified by the sample, and the resulting interferogram will have all the information concerning the vibrational modes of the sample. FT analysis of the interferogram will give us the spectrum in some seconds. As we have already mentioned, at the high energy side of the transmission window, absorption is due to electronic transitions, interband transitions. You remember the description of the electronic structure of a solid in terms of bands. Taking again the chemistry language, a band is obtained gathering together molecular orbitals. A sodium crystal may be constructed from isolated sodium atoms. Two sodium atoms will lead to a diatomic molecule with the valence 2s electrons occupying two molecular orbitals, one lower energy bonding molecular orbital and one higher energy antibonding molecular orbital. Increasing the number of atoms of that molecule, the number of molecular orbitals will also increase. The huge number of molecular orbitals will form a band, in this case for the sodium atoms, an S band. The same holds for polyatomic molecules, with bands of different energies being formed. Forbidden energy regions for electrons will define the gaps. The energy difference between the lower energy band, the valence band, and the first excited one, the conduction band, will define what we call the energy gap. The size of the gap defines insulators, semiconducting, and conducting material. This is the model. The same model can be used to qualitatively explain the so-called quantum size effect, known for semiconductor nanoparticles, or quantum dots. In this case, we go from the solid, with its valence and conduction bands, to the molecule, with its HOMO, highest occupied molecular orbital, and LUMO, lowest unoccupied molecular orbital. Here again, we gather together the physics and chemistry languages. In this diagram, you can observe the increase in the band gap. CDS powders, for example, are orange in color for micron-sized grains. Decreasing the size of the crystals, one observes a yellow color for nanometer-sized crystals. Concerning materials, the interesting point here is that the quantum dots behave as surface matter, since most of the atoms are at the surface. This table gives you an idea of that feature. A 2.1 nanometer crystal of gold atoms will display 63% of the atoms at the surface. This nanometric size will lead to novel chemical and optical properties that are, in fact, at the heart of what we call today nanotechnology. These are some absorption and emission spectra of CdSe nanocrystals, cadmium selenide. The quantum size effect leads to shifts in the spectra as a function of the crystal size. But let's come back to the transparency window of solids. Sodium chloride is completely transparent in the visible. The energy gap is 8.5 eV, or 146 nanometers. Silicon is black. It absorbs visible light. The energy gap is 1.1 eV, or 1128 nanometers. It's a semiconducting material, the base for our photovoltaic cells. These are the absorption spectra for these two materials. The cutoff wavelength is the equivalent to the energy band gap. A solid with band gap Eg has a cutoff wavelength defined as this expression. The solid will absorb photons of wavelength shorter than lambda c, higher energy photons, and be transparent for photons with wavelengths longer than lambda c, the lower energy photons. At this table, you will find the value of the energy gap for some materials. It shows also exciton Bohr diameter that defines the smallest structure that will exhibit bulk behavior. These are the absorption spectra for some glasses. You see that materials displaying colors spanning the visible range can be prepared. At the lower energy side, the so-called multiphonon edge will define the transparency window. The simplest model for a bond is the one that considers atoms as mass spheres and chemical bonds as coils. The heavier the constituents, the lower will be the energy of vibrational modes, whose harmonics will define the multiphonon edge. In this figure, you see the multiphonon edge for silica, fluorides, and chalcogenide glasses. The multiphonon edge is not the only property that will depend on the vibrational mode's energy. In this figure, we have the Raman spectrum obtained for a fluorindate glass. The harmonics of the highest energy vibrational modes are the ones that will define the absorption edge, as we have already said. The other important consequence that we will explore in next sections is the depopulation or desactivation of electronic excited states. Vibrational modes will define the non-radiative transition rates between excited states in lanthanide ions, for example. The lowest the energy of the vibrational modes, the lowest the non-radiative decays will be. Glasses transparent in infrared may have interesting applications, for example in thermal imaging. As we have seen, chalcogenide glasses are transparent in the region around 10 microns. This is the spectral region of light our bodies emit due to the temperature. You can check at the internet how these systems work. Chalcogenide glasses are also transparent in the domain where the vibrational signature of most molecules lies, from 2 to 12 microns. In this figure, you see the range of mid-infrared transitions for various atmospheric pollutants. So we can use these infrared fibers to carry the optical signal from the spectrometer to the sample and back to the detectors. This is another example of application that you can find in the magazine Laser Focus World. You can use optical fibers to sense contaminants and water in soil. A cone penetrometer system using chalcogenide fibers is used. A chalcogenide fiber is connected to a head-end optical analysis system and is inserted into the soil to be tested. The infrared signals reflected from the soil and transmitted through the fiber to the FTIR equipment in a truck, for example, are used to identify the contaminant marine diesel fuel. So, to finish this third class, I leave you with some images of another beautiful region of our country, the Pantanal. You see here some animals and amazing views. Useless to say that you must visit the Pantanal. See you in the next class. Don't forget to answer the quizzes.